Okay, doing a two-block problem here. So the question is, given that we have two blocks, one sitting on top of the other, and these blocks rest on a surface with no friction, but these blocks have friction between one another with a static coefficient of 0.6, what is the maximum force we can apply to the top block such that they move together? That is, I want them to move together and for not the top block to slide off. This is going to depend on how strong the friction is here. If there's not enough friction and we pull too hard, that 5 kilogram block will slide off of the 10 kilogram block. What is the maximum force I can apply to the 5 kilogram block such that they slide together? After this, we'll switch it up and I'll put the force on the 10 kilogram block. So to start out with, here's the problem. I want you to hit pause, copy it out, and perhaps see if you can work your way through this on your own. So here's the 5 kilogram block. Pulling it forward, we have an applied force. Force of gravity will pull it down, and the normal force will push back up on this. See the blocks here? Gravity's pulling it down. The normal force is provided by the surface of the 10 kilogram block. We will also have friction on this, and friction will pull back. The reason why I know friction will pull back is Newton's first law. Consider that bottom block. That block is at rest. It's at rest and it will have this natural tendency we call inertia, this natural tendency to stay at rest. When the top block pulls forward on it, the bottom surface of the top block will exert the force of friction forward on the bottom block. As Newton's third law tells us, the bottom block will respond by pulling back, exerting a force back on this block. Now, please don't allow that to cause a misconception. It's not going to pull this block back. The force that this bottom block exerts is all onto the top block. So as the top block drags the bottom forward, the bottom block pulls back on the top block. This pull is not experienced by the bottom block, it's something that it is doing. So that bottom block is not being pulled back, it is pulling back that while being dragged forward. Okay, so the top block has a force of friction pulling it back, an applied force pulling it forward, gravity pulling down, the normal force pulling up. It's 5 kilograms, and we're using acceleration due to gravity is 9.8. So my force of gravity is 5 times 9.8. It is, I believe, 49. That makes the normal force pushing upward also 49. The force of friction is going to have a maximum value. So when we write down the force of friction, if it's static, this isn't necessarily the amount of friction that's being exerted at that time, but it is a cap. It is the maximum amount of friction available. And that maximum amount of friction available, which we're assuming we're at because we're finding the maximum applied force here, is going to be the coefficient of friction, which is 0.6, times the normal force, which is 49. So the maximum amount of friction is 29.4. And I'm now looking for the maximum applied force that I can have under these circumstances. Now, it's very tempting here. It is very tempting to say, well, that's the maximum value of friction, so the maximum applied force would be also 29.4 newtons. However, that creates a contradiction. Let me explain. If I pull forward with 29.4 newtons and friction is pulling back with 29.4 newtons, the net force on this block would be 0. And as Newton's second law tells us, if the net force is 0, the acceleration is 0. The first law tells us that as well. So if I pull on this, but not with sufficient force, that it's greater than that force of friction, then it will not accelerate at all. So there's something more that's happening here. Here's what I need to do. I need to put this on the shelf for now and consider my bottom block. So let's think of everything we know about that 10 kilogram block. The 10 kilogram block also has friction pulling on it. However, the friction on the 10 kilogram block, the bottom block, is not pulling it back. It's pulling it forward because the friction is between the two blocks. With friction between the blocks and the top block being pulled forward, that friction pulls forward on the bottom block. So the same force of friction that I had pulling back on my 5 kilogram block is pulling forward on my 10 kilogram block. So my force of friction is 29.4. That is not the friction of this block on the surface. Remember from the question, the friction of the block on the surface is 0. So I've got gravity pulling this down. I also have the top block pushing this down, and I have the normal force pulling it up. Now, I don't really care what these values are. If there was friction between the 10 kilogram block and the surface, then this would be important because I would use the normal force to find the force of friction. However, it is suffice to know at this point that these all just cancel each other out. See, that's 10 kilograms, so this is going to be 98. The top block pushing down on this pushes down with 49, and if I add those together, getting almost 150, it's 147. All that cancels out, and there's no net vertical force. Now, what force is pushing back on the 10 kilogram block? And the answer is nothing. There is something that may seem like a force. It has mass. And as you pull it forward, with the inertia of that mass, it has this natural tendency to not pull forward. So it doesn't go immediately. It needs to be accelerated. But there's not actually an external force on this block pushing it back. So our net force is 29.4 newtons forward. And as such, the acceleration of the bottom block is the net force over its mass, because F equals ma. It is 29.4 divided by 10, which makes it 2.94. So the bottom block has a forward acceleration of 2.94, but guess what? These blocks, they move together, which means all their kinematics variables are identical, which means that this also has an acceleration of 2.94. And that's forward. So, to recap, to solve this two-block problem, I looked at the top block to determine how much friction is between the top block and the bottom block. I then took that friction, applied it to the bottom block, pulling it forward as the top block drags it. And I said, if we have that much pulling it forward, what will its acceleration be? I found that acceleration, but under the assumption that they move together, I'm saying that this undergoes the same acceleration as that does. And with this acceleration, again, F net equals ma. So our net force is our 5 kilogram mass multiplied by 2.94 meters per second squared. So I've got 2.94 and a 5 kilogram mass, 14.7. So this is 14.7 newtons. Now, where does that fit in here? Is FA 14.7 newtons? No. Put 14 in here. with 29 pulling back, and that will imply to you that friction is greater than the applied force, and when I pull forward on this block, it actually accelerates backwards. That's not what's happening. This is the net force. This is the force that's left over when all these forces cancel each other out. So, our net force. Now remember, never draw the net force as an arrow attached to the block. It is separate. This is the ultimate arrow that you get when all those arrows have been considered. Our net force is 14.7 newtons forward. That means that the applied force is so great that even when you subtract 29.4 from it, you get 14.7. So the applied force minus the force of friction gives us the net force. Our unknown applied force minus 29.4 gives us 14.7. So our applied force is 14.7 plus 29.4. So it's about 55. So I've got 14.7 plus 29.4, and it gives us 44.1. So the greatest force that we could apply to the top block, such that these blocks don't slide apart, is 44.1 newtons.